This week's lab, a Diels-Alder cyclization reaction. These are considered electrophilic addition reactions in that we're using a molecule drawn to another one that has an electron-dense source, and we're breaking that electron density and putting two molecules together. Okay. And specifically, Diels-Alder react a diene and a dienophile. That is a molecule with two double bonds and another molecule that's drawn to it. For Diels-Alder, by the way, that dienophile will have at least one unsaturation itself, a double or triple bond. Okay. These always give you one more ring than what you started with, hence the term electrophilic addition or cyclizations. Okay. The diene has to be in the boat, cis-boat conformation. The trans would give you a new six-membered ring that is sterically basically impossible. So we have to have the diene in the cis conformation. Electron withdrawing groups on the dienophile increase its reactivity, and electron releasing groups like methyls, etc., on the diene increase its reactivity. So this tells us when we get to the mechanism that we really want to start with the diene, as alkyls hook to the carbons in the diene, allow them to, the carbons, to take those pi electrons and go and start the mechanism. Whereas the electron withdrawing groups in the dienophile mean that as those electrons get pulled away, the carbons where they're attached are more enticing for the diene to go react with. Right? So the reaction mechanism for today. So cyclopentadiene and maleic acid. Here again, the diene is in the boat conformation within the ring, and then the unsaturation, the two carbons in this pi bond, are the dienophilic portion of our other molecule. Okay? So we're going to take the pi bonds from one of the dienes pi bonds and attack one of the carbons in the dienophile. Okay? Now, that carbon already has four bonds. Don't forget there's a hydrogen there we don't picture because of the bond line. Okay? But that carbon has four bonds. It has to do something. As it accepts the new bond, it has to let go of the old bond. Okay? We'll get with that in just a moment. Meanwhile, if this were all I were doing, and I wanted to draw an intermediate, this carbon would be the one to get control of the electrons, leaving this carbon as a carbocation. Okay. The rest of the maleic acid. Okay. If this carbon is the carbocation, then it can be resonance stabilized. If it were the other way around, the resulting carbocation would be too far away from the pi bond that's left in our diene to be resonance stabilized. Okay. However, because of stereochemistry and other things, we know that it doesn't stop. We're not going to generate a carbocation. Okay? But I only said that so that we would understand that it's this carbon from the end taking control of the electrons and making the new bond to this carbon in the dienophile. Here again, that carbon has to let the pi bonds go. It has to let go of something, and the best choice being the weak pi bond. So the other carbon that had been in the pi bond is going to take them and attack the carbon number 4, if you will, in our dienophile. That carbon already has 4 bonds, has to let something go. Best choice is the weak pi bond. So the carbon here takes these electrons and flips them off. Remember, we said this carbon was, if we stopped to do an intermediate, would be a carbocation. Okay, so we dislike circular mechanisms Okay, this certainly is one, but there are times when that is the best explanation. And here again, because of stereochemistry and some other things that you should be talking about in lecture course, we know that Diels-Alder cyclizations happen in one concerted step. Okay? There's no intermediates, if you will. So if I number the 6 carbons that were involved in the actual mechanism, they're going to produce a new 6-membered ring. In addition, there's 1 carbon hooked to what are the numbered in orange 1 and 4. So I have a 1 carbon bridge there. And then over here I have the rest of the maleic acid. And the only other thing that I'm missing is the new bond between carbon 3 and carbon number 2 in the way I numbered it before. So there's our product. Procedural notes for the Diels-Alder reaction. A gram of maleic anhydride and 4 mils of ethyl acetate in a small Erlenmeyer. Swirl it to dissolve. 4 mLs of Lagroin, also known as PET ether. PET stands for the way petroleum, and even that is a sort of misnomer. It is the first layer off petroleum distillations when crude oil is turned into gasoline, and so it's a mixture of hexane isomers. Add a milliliter of cyclopentadiene. That you will find in input 5, as cyclopentadiene itself undergoes a dimerization, a Diels-Alder style reaction, which can be undone with slow heating, and then the cyclopentadiene isolated through distillation. That will have been done for you this morning, okay? If upon addition of the cyclopentadiene, it solidifies much like a gel, then gently warm it. If not, keep swirling it. If it doesn't at all, then swirl it for a bit and then chill it on ice. Collect the crystals via vacuum filtration. Allow them to air dry in your drawer for a week. Get a melting point on it. Get it in a sample vial. Get it correctly labeled with a blue label and turn it into the blue basket by midterm, as that's one of your products. Also realize that you need to make sure and get a reagent card from me for next week, which is the Friedel-Crafts acylation of an aromatic substrate. And we're going to use different substrates around the lab. That way you don't have to write up 6 different aromatics when you're only going to use 1. The crystals, if you look very closely, okay, and I'll have this available to you in the lab, this is through the mouth of a small Erlenmeyer. So he took the picture right down, but they're very fine, needle-like white crystals. Very nice product today.